Greetings for the day. So welcome to the video lecture. So myself, my name is B. Karthik, working as an assistant professor in the Department of ECE, MITS, Madanapalli. So in this video lecture, we will discuss about the different network theorems applied to the AC circuits. So next slide. So this is our flow of presentation. So network theorem in the sense, we will discuss about the statement of superposition theorem, Thevenin's theorem, Norton's theorem, and one simple problem we will discuss for each and every theorems. So what is meant by a superposition theorem? So according to the theorem, it states that the voltage across or current through an element in a linear circuit is the algebraic sum of the voltages across or current through at that particular element due to each independent voltage source acting alone. So the idea of the superposition theorem is based on the linearity principle. So linearity principle in the sense, we have different number of, in our electrical circuit we have different number of independent sources are there. So like independent source in the sense, we can take it as so like this, there are more independent sources are available in our electrical circuit. So we have to find the particular current through the particular branch. So we need to follow the superposition theorem statement. So it helps us to analyze a linear circuit with more than one independent source by calculating the contribution of each independent source separately. So next, now let us look at one problem based on the superposition theorem. So this is our problem. So verify it by using superposition theorem. Determine the current through the 3 plus 4j ohm resistor. So we are having two sources, voltage sources V1 and V2, and this is nothing but the R1 resistance and impedance in this inductance, and we are having R2 L1, that is 3 ohm, and 4j ohms are there. So what are all the steps followed in our superposition theorem? So step number 1. So we need to consider the V1 voltage source, that is 5 angle 90 voltage source V1. Consider this source. So consider this source 5 angle 90 voltage sources. So this is a we have to consider, and we have short circuited this voltage source. So we need to find the current through this 3 plus 4j ohm resistor impedance. So how to find? So directly we know that we have to find the equivalent resistance which is which is followed in our circuit diagram. So we can able to find this 3 plus 4j ohm resistor impedance value. This will be parallel with your inductance, and this entire combination will be connected in series with our 5 ohm resistors. So look at the calculation. So equivalent resistance, that is equal to 3 plus 4j ohms into 5j divided by 3 plus 4j plus 5j ohms. So collectively we are getting the answer as this value, and this will be, that is this combination of this one. So this will be added with our 5 ohm resistor. So collectively we are finding the value for R equivalent is equal to 5.833 plus 2.5j ohms. So next one, we have to find the current for the this 3 plus 4j ohms. So next, up to this we found the equivalent resistance value for the circuit. Next, we need to find the current value, total current of the electrical circuit. So I is equal to V1 by R equivalent, that is we are having 5 angle 90 volt, that is it is in the polar form, divided by 5.833 plus J 2.5, it is in the rectangular form. So if you divide these two value, we are getting the value as 0.310 plus J 0.724 amps. Next, we need to find the particular current for the particular current for the particular resistance plus the inductance value. By using the current division rule, the current flowing through the 3 plus 4j ohm is nothing but, we know the current division rule how to find means, I1 is equal to the total current, that is I is nothing but the total current into which one is parallel to this total current. So 5j is the parallel, that is 5j divided by sum of the impedance, that is 3 plus j9, we are having that answer. If you see this problem, we can able to find this value. And this is our total current into J5 divided by 3 plus J9. So if you use the calculation means, we are getting the answer as rectangular form. So 0.0344 plus J 0.34413 amps. So next one, step number 2. So previously what we consider means, consider V1 source we consider. So V1 source we consider, but step number 2 la we have to consider V2 source and can short circuit this V1 source. Short circuit to be V1 source. So what is the value means, V2 is nothing but the 50 angle 0 and short circuit V1 is equal to 5 angle 90 volt source. So find the same current we have to find. Let us take it as a I2. So R equivalent is equal to the same thing. We in this circuit diagram the combination will be different. So this 5 ohm is parallel with our R2 plus L1, that is 3 ohm plus 4J ohms. So if you calculate this value, we are getting the answer as 2.5 plus J 1.25, and this combination will be series with our J5 ohms. So we are getting this answer. So collectively we are getting answer as equivalent resistance is equal to 2.5 plus J 6.25 ohms. So next we need to find the current, total current for this circuit. So we have to find that I2, that is I2 is equal to, what is the value? So V by R equivalent. V by R equivalent. So I2 is equal to that V voltage is nothing but 50 angle 0 divided by 2.5, this value 2.5 plus J 6.25. So let us look at the next one. So we are getting the answer as 5.50 angle 0 divided by 2.5 plus J 6.25 ohms. So we are getting the answer as 2.5758 minus J 6.896 amps. So this is our I current, that is total current. So by using the current division rule, our final objective is the current flowing through the 3 plus 4J ohms. So I2 is equal to, we are having the total current into which one is parallel, 5 ohm is parallel divided by sum of the resistance and inductance. So 8 plus J4 we are getting. So this is our total current into 5 divided by 8 plus 4J ohms. So we are collectively we are getting answer as minus 0.344 minus J 4.1379 amps. So now up to this step number 1, step number 2 completed. Now according to the superposition theorem, our ultimate aim is to find the current for the particular resistance, that is 3 plus 4J ohms. Next, how to find? So I is equal to total current, I is equal to I1 plus I2. So whatever the answer we found previously, that we have to add. So 0.0344 plus J 4.413 plus minus 0.344 minus J 4.1379. So collectively we are getting answer as I value. This is our total current flowing through the particular resistance plus inductance. So now this total current is in the rectangular form. This total current is in the rectangular form. So we have to convert this rectangular form to polar form. So by using with the help of calculator, we can able to convert this value as I is equal to 3.73 angle of minus 94.16 amps. So this is our simple problem for our superposition theorem. How to do for the theorem this based on AC circuits. So next theorem we are going to discuss about this Thevenin's theorem. So Thevenin's theorem is nothing but Thevenin, it was developed in 1883, which is with the help of scientists, that is named as M. Leon Thevenin. So 1857 to 1926, a French telegraph engineer. So he only founded the Thevenin's theorem. So what the theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consists of a voltage source in series with a impedance. That is the statement of Thevenin's theorem. So what is the meaning of this VTH means? VTH is nothing but open circuit voltage at the load terminal. ZTH is nothing but equivalent impedance at the terminals when the independent sources are turned off. So now let us look up for the example for the Thevenin's theorem. So verify it by using Thevenin's theorem. So determine the current in 5 ohm resistor and we have to draw the equivalent circuit diagram. So in this I am giving the V1 voltage source as 10 angle 0. 10 angle 0 volt. I didn't mention, but V1 is equal to 10 angle 0. So this is our R1 5 ohm and the same thing 3 ohm, 4J ohms, J5 and 5. So this is our load terminal. This is our load terminal. So our objective is to find the current through the load terminal, that is 5 ohm resistor. We have to find the current through the 5 ohm resistor. So let us look at steps. What are the steps available for the Thevenin's theorem? Step number 1. First of all, we have to find the Thevenin impedance. So what is the procedure for Thevenin impedance? First of all, remove the load terminals. Remove the load terminals. And short circuit the voltage source, that is V1. Short circuit the voltage source. V1 is equal to 10 angle 0. So we have to find the Thevenin impedance, that is ZTH value from the load point of view. That is why I am mentioning like arrow mark putting like this. So we have to find the Thevenin impedance from the load point of view. So what is the meaning? So ZTH, how to find? ZTH is equal to this 5 ohms and this 3 plus 4J are parallel connection. So parallel connection in the sense we know that R1 R2 divided by R1 plus R2. So we have to do that 5 into 3 plus 4J divided by 5 plus 3 plus 4J, and combination, this entire combination will be in a series with 5J ohms, series combination. So we are getting answer as ZTH is equal to 2.5 plus J 6.25 ohms. This is our Thevenin impedance. So our objective is to find Thevenin impedance means only in our electrical circuit only the resistance inductance only present, not like a independent voltage source or not like a load terminal, everything should be removed. So only we have to find the Thevenin impedance from the circuit. So next one, step number 2, how to find the Thevenin voltage. So Thevenin voltage or open circuit voltage, we can say it as Thevenin voltage or open circuit voltage, that is VOC, open circuit voltage. So how to, what is the procedure for this? Open circuit the load terminals, the same thing, open circuit the load terminals and find the voltage across this 3 plus 4J ohms. So why we are finding this voltage across these 3 plus 4J ohms means we are already removed the load terminal. So we need to find the open circuit voltage means across or parallel to the load terminal, which terminals are there? There is 3 plus 4J only are there. So we need to find the open circuit voltage for this 3 plus 4J. So how to find? VOC is nothing but the VTH. So 10 angle 0, 10 angle 0 is nothing but we are having this this value into 3 plus 4J divided by 5 plus the entire thing, 5 plus 3 plus 4J. Like you know, before that we have discussed about the current division rule. The same concept only we are applying for this open circuit voltage. So we are having the total voltage, supply voltages are there, and 3 plus J4, which one is parallel, divided by sum of the resistance. So we are getting the answer as 5 plus J 2.5 voltage. This is our open circuit voltage or Thevenin voltage. So next one, finally step number 3. Oh, before that, convert the rectangular form of the Thevenin voltage to the polar form. So with help of calculator we can able to find this answer. Next one, what is our ultimate aim? We need to find the current through the load terminals. So what is the formula? This is our formula. IL is equal to VTH divided by ZTH plus ZL. Thevenin voltage divided by Thevenin impedance plus load impedance. So in that load impedance we are having only resistance. So that is why I collectively mention as ZL, or else we can mention as RL also we can mention. That is nothing problem. VTH 5.6, ZTH 2.5 plus J 6.25 plus 5 ohms. So using a calculator we can able to find the answer for this one, load current IL. So this form also it is represented in our rectangular form. Rectangular form only it is available. So we have to convert it to polar form. So with the help of calculator we can able to find the answer for this one, I value. So I is equal to 0.573 angle of minus 13.25 amps we are getting. So next one, finally we have to draw the equivalent circuit for the Thevenin's theorem. How to draw the equivalent circuit? The same thing, VTH which is in series with our Thevenin impedance. Series connection. It is in a series connection. So open circuit voltage is connected in series with a Thevenin impedance. Like this we have to draw the equivalent circuit for the Thevenin's theorem. Next one, we will discuss about the Norton's theorem. So previously that one of the scientists, that Leon Thevenin, founded the Thevenin's theorem in the year of around approximately 40 to 40 years before he found. Then after that in 1962, about 43 years after this Thevenin's theorem, he published one theorem named as E.L. Norton, one of the scientists. E.L. Norton, an American engineer, he is worked as a worked at Bell Telephone Laboratories. He proposed the similar theorem, name it as a Norton's theorem. So what we discuss for the Thevenin's theorem ultimately we have done for voltage. Norton's theorem is applicable for current. That's all. So what is the theorem statement? According to the theorem, it states that a linear two-terminal circuit can be replaced by a equivalent circuit consist of a current source, that is Norton current IN, in parallel with our impedance, that is Norton's impedance ZN. So IN is nothing but the short circuit current through the terminals, and ZN is nothing but the input or equivalent impedance at the terminals when the independent sources are turned off. So we need to find the IN as well as ZN value. So let us look at an example for the Norton's theorem. So verify it by using Norton's theorem. Determine the current in 3 ohm resistor, that is load resistor. So previously we have taken as a 5 ohm resistor. So in this we are replacing that load resistor, load terminal, and draw the equivalent circuit for the Norton's theorem. So in this case we are using V1. So V1 I think so 5 angle voltage source we have given. So let us look up, and this one is 3 ohms J4 and 4 ohm minus. In this we are using capacitance. So previously we are not included capacitance. So this case we are using capacitance. What is the step number 1? Step number 1 is nothing but to find the Norton's impedance. So we need to remove the load terminals. As we know, we have to remove the load terminals, and whatever may be, we are having short circuit the voltage source 10 angle 0. Okay, previously I have mentioned at 5 10 angle 0. So 10 angle voltage source we have to short circuit. So we have to find the Thevenin impedance, that is Norton impedance. So Zn is equal to, you know that this 3 plus 4j and this 4 plus 4 minus 5j are in parallel combination. So we need to find the impedance, Norton's impedance from the load point of view. So this will be parallel combination. You know that this one is one value, this one is another value divided by sum of these values. So we are getting the answer as ZH, Zn is equal to 4.46 plus 0.78 ohms. So next one, what is step number 2? Step number 2, previously in Thevenin's theorem to find, we found that open circuit voltage. But in this Norton's theorem, we are going to start with Norton's short circuit current, IN. Norton's or short circuit current. So previously we have opened the load terminals, but in Norton's theorem we need to short circuit the load terminals, IN, that is 3 ohms we have to short circuit. So in this we are giving V1 is nothing but the 10 angle 0 volt, this 3 ohm, and J4 is there. Oh, sorry, 25. Okay, 25. I just mistakenly mentioned 25. So 25 angle voltage divided by 3 plus J4. So we have to find the Norton's current. Norton's current in the sense, this is our Norton's current. We have to find. So IN is equal to 5 angle minus of 53.13 amps. This is our IN value, Norton's current. Next one, step number 3. What is step number 3? Find the load current. Load current flowing through the 3 ohm resistor. So IL is equal to IN. What is the answer we are getting? IN into Z10 divided by Z10 plus ZL. So this is nothing but this is the formula for the current division rule. Current division rule concept. Suppose if we want to find the particular current for the particular resistance, means we need to find the total current into parallel resistance divided by sum of the resistance. The same thing only we are doing for the load current for the Norton's theorem. So 5 angle minus 53.13, and this is our parallel Zn divided by this value. So we are getting the answer for this one, 1.972 minus J.2.284 ohms. With the help of calculator we can able to get this answer. Next, this rectangular form, we need to convert this rectangular form everything. So this have to convert it to rectangular form to polar form. So we are getting answer as 3.017 minus angle of minus 49.19 amps. So this is our load current for the Norton's theorem. Next, what is the next case? We need to draw the equivalent circuit for the Norton's theorem. So previously we have drawn voltage source in series with the Thevenin impedance. Now we have to draw the equivalent circuit like this. Norton current which is parallel with our Norton impedance. So this is our equivalent circuit for the Norton's theorem. So far we discussed about the two theorems we discussed. Superposition theorem, Norton's theorem, Thevenin's theorem, everything we discussed. So for all the theorems, our ultimate aim or our ultimate objective is we have to find the current through the particular value. Anything, load or anything we can take. All the theorems, our ultimate objective is to find the particular current in particular resistance. Everything are same. So in our next class, we will discuss about the next theorem is nothing but maximum power transfer theorem are there. So maximum power transfer theorem is the sense we need to find the maximum power delivered to the load. We need to find, we have to, the same thing, we have to go for the statement, and we will look at some simple example for the maximum power transfer theorem. And some other theorems are the Teligand's theorem, reciprocity theorem also available. So we will discuss for the AC circuits. Thank you.